Ladies and gentlemen, this is Unit 5, and prerequisite skills for Unit 5 are, number 1, classifying polynomials. Classifying polynomials. What does the word classify mean?
To describe?
Yeah, like describing. Anything else?
Define.
Defining, grouping. Okay, when we classify something, we're usually grouping. So basically, it's just a way of naming or identifying polynomials. You can classify a polynomial by its number of terms, or its degree. And we'll explain what that means as we go. So we can classify it by its number of terms or by its degrees. Now, the degree of a polynomial is the greatest degree of any of its terms. The degree of a polynomial is the greatest degree of any of its terms. So if we look at a polynomial, any of its terms, and it has multiple terms, we could name it after its number of terms, or we could look at each of those terms, see which term has the greatest degree, and then that's the degree of the whole polynomial. And we'll do a couple of examples as we go. The next sentence you have there, the degree of the term is the sum of the exponents of its variables. And that's a big mouthful, but it's pretty simple when you break it down. Let's say you had the term 2 times x times y squared times z. That's one term because it's glued together by multiplication, right? And we realized a polynomial was a chain of terms linked together using subtraction or addition. So this is just multiplication, which makes this whole thing one term. Now, the degree of this term is the sum of the exponents of the variables. So here I see we have a digit, 2. That's a value, that's not a variable. I have a variable here, here, and here. 3 variables, x, y, z. The exponent of the x variable is 1. The exponent of the z variable is 1. And the exponent of the y variable is 2. So the sum means I'm adding these guys up. 1 plus 2 plus 1 is 4. So the degree of this term is fourth degree. Okay, let's try a couple of examples. You have a chart there, a blank chart.
Then why is 2? Why is y 2?
There were 2 y's.
Where are we supposed to write?
So I just got asked the question, what does this mean? This means y times y.
Oh.
So basically, x to the power of 1, y to the power of 2, z to the power of 1 is the same as x times y times z. 4th degree.
Yeah, but wouldn't y have to be 2 times? So it'd be
Y is 1. Can't be 1.
Okay, the first example that we would like to do is in your box there, the top box. You can put in this value, 2 times a times b times c. So that is one term. So you can put that in the polynomial column. Now, if we were going to classify this polynomial by its number of terms, how many terms do you see?
1.
1. So this is a monomial. And you have enough room there to put monomial in the top of the box. And then just say because, like b slash c, it has one term. If we were going to classify this by its degree, what would we say? Well, we need to look at the polynomial, pick the term with the greatest degree. There's only one term, so that's easy. And determine the degree of this term, which is just the sum of the exponents of the variables. So this would be a third degree. Good job. Okay, let's look at 7x squared plus x. If we had to classify this by the number of terms, what do we see? Yeah, I see 2 terms. If it has 2 terms, it's called a binomial. Nice. Binomial, and then underneath b/c, because it has 2 terms. And what about the degree of this polynomial? So we're
Second, why don't you just add the x to x squared?
we're only adding the exponents of one term. So we pick the term that has the greatest degree. Is it 7x squared or is it x? It's 7x squared, and the degree then is second degree.
Can you just add the x to x squared and we get x cubed?
Note, because x cubed means x times x, not x times x plus x. Very different. Good question. Good, let's look at a third example. This one's going to be a bit long and ugly. We've got 7k squared m plus 15k cubed m squared minus 6k m squared. Now if we had to classify this by its number of terms, what would we say? Trinomial. Yeah. Often anything over a binomial just gets called a polynomial, but we can use trinomial as well. Trinomial, BC, because has 3 terms. And in order to classify this by its degree, we first need to identify the term that has the greatest degree. So we're looking at 15k cubed m squared. And then it's the sum of the exponents of the variables. So we're just adding up 3 and 2, which is 5. Which makes this a 5th degree. Okay, 2 ways to classify polynomials. Make sure you keep that language clear and organized in your thinking so that we can use it. The next section in getting ready is adding and subtracting polynomials. So to add polynomials, we first take care of the brackets. And then, second, we collect like terms. First we're going to take care of the brackets, then we're going to collect like terms. And let's look at an example. We're going to do 2 examples. The first one is 2x squared plus 3x minus 5, close bracket. And that's getting added to, in brackets, 7x squared minus 6x minus 2. And just go and double check that you have the same thing that I have. Otherwise it won't make much sense. Now, if there's an addition sign here, if there's no addition sign and it's just a bracket beside a bracket, we're dealing with multiplication. But here we're not dealing with multiplication. We're dealing with addition. But we have to remember that this plus sign gets applied, distributed to each term in this bracket. Now with a plus sign in front, that's really easy because it doesn't change anything. This is just going to be equal to, taking care of the brackets, 2x cubed plus 3x minus 5 plus 7x squared minus 6x minus 2. Now a question that often gets asked,
Is it 2x squared?
2x squared, good call. The question often gets asked, hey, Mr. V, why can't I just add these guys up right here? They both have x's in them. Can't I just add 2x's and 3x's and that'll be good? No, you can't, because x squared is totally different from x. Okay, they're not the same. X squared means x times x. That would be like saying, Mr. V, if x was 4, then this one would be, x would be 4, and this x squared would be 16, right? You can't add those together. They're different values. So you don't have 5 x's. You have 2 x squareds and 3 x's. But now that we've taken care of the brackets, we can collect like terms. So I notice I have an x squared term here and an x squared term here. I have an x term here and an x term here. And I have a constant here and a constant here. So when I group those together, I have 2x squared plus 7x squared. That's 9x squared. Then I have 3x minus 6x. That's negative 3x. And negative 5 minus 2 is negative 7. And that is a polynomial simplified. Subtraction works in a very similar way, but we have to make sure we take care of the brackets first again. So here's an example with subtraction. Our first bracket is 4a squared plus 5ab minus 9b squared. And this time we have a minus sign in between the brackets. And inside the second bracket is going to be 7a squared minus 6ab plus 2b squared.
Is that minus 5ab?
Over here in the first is a plus. Yeah. Well, now we need to be careful not to get tricked, because this minus sign is really like a minus 1, and it's multiplied by that second bracket. So this negative 1 needs to distribute to each term inside that second bracket. So let's go ahead and rewrite this and see what it looks like after we've done that. Nothing changes in the first bracket, so we can get rid of those parentheses. 4a squared plus 5ab minus 9b squared. But then in the second bracket, we're going to lose the parentheses, but now instead of 7a squared, we have minus 7a squared. Instead of minus 6ab, we have plus 6ab, and you'll notice just the signs are all changing. We have minus 2b squared. Now again, just like before, we're going to group like terms. I see I have an a squared term here and an a squared term here. Always keep the sign that belongs to the term. Okay, so this negative sign belongs with 7a squared. Then we have 5ab and 6ab, and then we have negative 9b squared and negative 2b squared. So grouping like terms, we have 4 minus 7, negative 3a squared. 5 plus 6, 11ab. Negative 9 minus 2, negative 11b squared. And that is as simplified as that one gets. Okay, when we're dealing with the product of a polynomial and a monomial, all we need to do is use our distributive property. So that's your blank there. Use the distributive property. And we're going to take some notes on the distributive property in 5.1. But you should be fairly familiar with it already. All we need to do is multiply the monomial, in this case, by each term in the polynomial or the binomial. So in our example, we've got 2 times x plus 3. This, it's just one number, but it's a term in a polynomial. It's a monomial, right? It's a polynomial with one term. And it's being multiplied by this, which is a binomial. It's a polynomial with 2 terms. So what we're told is that all we have to do is distribute. Multiply each term by each term inside the brackets. Which means we're left with 2 times x, which is 2x, plus 2 times 3, which is 6. 2x plus 6. Let's look at another example with a negative out in front. We have one term, a monomial of negative a, and we're multiplying that by a binomial, 3a plus 5. All we need to do is distribute this negative a to both terms inside the binomial. So we get negative a times 3a. Okay? Good. So we've got the negative sign changes the whole thing. It's a negative times a positive, so we've got negative. The number part, the numerical part of the term is just 1 times 3, which is 3. And the variable part is a times a, which is a squared. Then the same principle applies here. We've got a negative times a positive, so it's going to be a negative. And we've got a times 5. That means we have 5 a's. And that one is done. All right, the factors of 12. So that means anything that can get multiplied by anything else and the product be 12, those numbers are factors. So you can multiply 1 by something to get 12. You can multiply 2 by something to get 12. You can multiply 3 by something to get 12. You can multiply 4 and 6 and then 12. Those are all of the factors of 12. 5 is not a factor because there's nothing that can be multiplied by 5, not a whole number, to get 12. Okay, and anything bigger than 12 couldn't possibly be a factor of 12. Basically what we're saying is these are the numbers that can be multiplied by each other to get 12. I like to think of it, if I'm doing a list of factors, I kind of think of it as a hill. You go up the hill to halfway, like to your, and then you go back down and get every matching factor. So for instance, we would be like 1, 2, 3, and then on the other side of the hill is 4, because 3 and 4 multiply to 12, and then 6, because 2 and 6 multiply to 12, and then 12, because 1 and 12 multiply to 12. And then you're done. So if you get all the factors going up the hill, going down the hill is really easy, and then it's done. That's all the factors. Okay? We also need to talk about greatest common factor. Greatest common factor. To find the greatest common factor, or GCF, of two numbers, you need to represent each number as the product of its primes. Product of its primes. Now, who knows what a prime number is?
A number that can't be multiplied.
Only divisible by 1 and itself. So for instance, the number 3 can only be divided by 1 and 3, not 2. 2 is not a factor of 3. Or the number 11. There's no numbers that will multiply to 11 except for 1 and 11. Can you think of another one? 5. 19. 17.
13.
13. Yep. 23. They will all be odd because an even number is always divisible by 2.
Yeah, but not 27.
It's because 27 is odd, but it is divisible by 3 and 9, right? Good. So now we know what a prime number is, and we want to represent each number as the product of its primes. So look at what happened. We want to find the GCF of 12 and 18. So we're going to take the number 12 and the number 18, and we're going to represent them as the product of their primes. So we're going to break them down as small as we possibly can, and they're going to be a product. So we're breaking them down into their factors. Okay? So 12, I can divide 12 by 2, and I'll have 6 left over. And I can divide that 6 into 2 times 3. Okay? I've now represented 12 as a product of its primes. These are all primes. 2, 2, and 3 are primes. Let's double check to make sure that it does still equal 12. 2 times 2 is, times 3 is, boom. Okay? Let's look at 18. Somebody divide 18 by something for me. So it could be 2 times 9? Yeah? Okay, so 2 is a prime number. What about 9?
2 times 3 times 2. No.
9 can still be broken down into what? 3 times 3.
2 times 3 times 2.
So the primes, 18 as a product of primes is 2 times 3 times 3. Now, we need to look for common factors. Common factors. Between the list of factors for number 12 and the list of factors for number 18, are there any common factors? Yeah, they have 2 in common, right there and right there. I can't circle both 2's. I'm doing a 1-to-1 match, and they have 3 in common. That means that their greatest common factor is 2 times 3, or 6.
Mr. B, couldn't you just do it like you're labeling all the...
So when you're in a situation where you need to represent a number as a product of its primes, you can use this strategy for prime factorization. That means splitting a number into its primes. Somebody pick a decently big number between 50 and 100.
51, 75.
An even number.
76.
Sure, 76. I don't think that's going to be a very interesting one, but 76. I know right away it's divisible by 2. So I can split 76 into 2 times, what?
24, 39,
38, right? Now this is a prime. 2 is already a prime. So now 38 I can split into what? Well, it's even. Well, close. It's even, so I know I can divide it by 2, and it's going to be 2 and 19. 19 is a prime number, that's why this was kind of a boring one. But the prime factorization of 76 is 2 times 2 times 19. And that will work for any number in the whole world. Okay? Using that strategy to get its primes. Okay, ladies and gentlemen, we're going to look at multiplying polynomials through examples using algebra tiles. So algebra tiles are a physical tool that you can manipulate and move around. We have digital ones online that you can move around, so you can kind of picture what's happening with these multiplying of polynomials. One key thing that you need to know is that algebra tiles are like this. We've got a block, a line, and a big block. This little block just represents 1, like not like 1 unit. It's just the number 1. So if you're adding 1 plus 2 plus 3 plus 4 plus 1 plus 2, you'd be adding blocks. The stick is x. Is x. Okay, we're not learning about the base 10 system. It's not 1 1000. Sorry. And if this length is x, well, then that makes this length x and this length x, which makes this box represent x squared. X times x. The area of this box is x squared. Okay? So when we're talking about algebra tiles, that's what you need to remember. Good.
Let's go
Example
online
1, we're using algebra tiles to model the product of, first, 3x times 2x plus 1. So you have your grid drawn for you there. We need to put one of our polynomials in the vertical space and one in the horizontal space. It does not matter what you put where. I'll do the first one with you, and you're going to be expected to be able to draw the second one on your own. So, remember, x's are bars. So on the vertical, I'm going to do my 3 x's. I'm going to make sure they're generally the same size and shape. 3 x's. And down at the bottom, I have 2 x's plus 1. Well, let's look at what happens. Here I have x times x. Here I have x times x. Here I have x times x, x times x, x times x, x times x. So these are all x squareds. All these big boxes are x times x, which is x squared. Now what I have left is x times 1, which is 1x, so a bar. And then I have x times 1, which is 1x, and then I have x times 1. All of these are just x. So in orange, I have my product. I have 6x squared plus 3x. Go ahead and try your second one there. Use Algebra Tiles to model the product of x plus 2 times 2x plus 3. So choose one of your axes to be x plus 2 and the other one to be 2x plus 3.
Does it matter?
It does not matter, but you should be able to look at the one that's longer and do the statement that's going to be longer there. Finish out your multiplication and you can check the board to see if you got the right answer in a minute or two. Okay, go ahead and double check the board to see if you did it correctly and you got the correct final answer of 2x squared plus 7x plus 6. Now you know how to multiply polynomials using algebra tiles. We're going to quickly learn about the distributive property and then do a couple of examples using the distributive property. Okay, the distributive property is an algebra property. An algebra property used to multiply polynomials. It's an algebra property used to multiply polynomials. So we can take a first really easy example and just look at what happens when we have two polynomials. Let's say the monomial 2 times the binomial 3 plus 6. We're going to look at this in two different ways, just to show that the distributive property works and always works. We could solve this using BEDMAS. Or we could solve it using the distributive property. Okay? If we use BEDMAS, we need to deal with what's inside the brackets first. So 2 times 3 plus 6 would end up being 2 times 9, which would equal 18. If we use the distributive property, which in this case is not easier, but it is when you're dealing with variables, means we're distributing the 2 to both terms inside the binomial. So 2 times 3 plus 6 means we're doing 2 times 3, which is 6, plus 2 times 6, which is 12, which equals 18. Did we get the same answer both ways?
Yes.
Yes, we did. Well, let's look at this in the case with variables. Let's look at 2 times 3x plus 6. So it's a similar problem, but this time we have an 3x instead of a 3 by itself. If we look inside this brackets, we need to deal with the brackets first, right? But 3x and 6 cannot be grouped. They are not like terms. They have different variables. 6 is just a constant. It's just a number value. This means that there are 3 x's. 3 x's. X plus x plus x. So what do we do here? We can use the distributive property, which means we're distributing that 2 to both terms inside the binomial. 2 times 3x is 6x. 2 times 6 is 12. According to the distributive property, this statement is equal to 6x plus 12. Okay?
You can't use BEDMAS? You can't even use BEDMAS for that?
We did technically use BEDMAS, but once you can't group anything more inside the brackets, then you go to multiplication. And we distribute it. Yep. Okay, let's do a more challenging example. Let's do two binomials. Yes. we've got two binomials. Let's say we've got x plus 2. We're going to multiply that by x plus 5. Now what this means is that we're taking both the terms in the first set of brackets, both the terms of the first factor, the first binomial, and multiplying it by both of the terms of the second. So what that really means is we're going to have x times the second bracket, and we're going to have 2 times the second bracket. And now we can distribute the monomial to both terms inside the binomial. X times x is x squared. X times 5 is 5x. And the same thing on this second one. 2 times x is 2x. 2 times 5 is 10. And now we can group our like terms. We only have one x squared term. We have two x terms. 5 plus 2 is 7. And we have a constant of 10. Now who knows a faster way to get from here to here? I heard someone say it, is why I'm asking. FOIL.
Oh, first inside, outside, last.
First times first, outside times outside, inside times inside, last times last. So let's go ahead and look at, let's see what this looks like if we FOIL it. X squared times x plus 5. And we're going to FOIL it. So here we have first times first, that's x squared. Outside times outside, that's x times 5, which is 5x. Inside times inside, 2x. Last times last, 2 times 5 is 10. Group like terms, x squared plus 7x plus 10. So we get the same answer. FOILing is the application of the distributive property. Okay? And it works for monomials, binomials, trinomials. It works for all of them. Just if you're doing it with a trinomial, there's more terms to multiply by the other thing. So you're not actually FOILing. You're making sure that every single term in one bracket gets multiplied by every single term in the other set of brackets. Okay, looking at example number 2, which is just using the distributive property. Here we go. We're going to find each binomial product. I'm going to leave A alone. You can do A by yourselves at some point. I'm going to do example 2B. In B, we're given the factors x minus 2 and x plus 4. And all I need to do is use my distributive property, which means I'm FOILing that. So sometimes if I'm just getting used to doing it, I will write FOIL so that I make sure I account for all of the terms that I need. First times first means x times x, which is x squared. Outside times outside. And you can see by those arrows that this x has now been multiplied by both of the terms in the second bracket. So x times 4 is 4x. Now we have inside times inside. That's negative 2x. And last times last. Oh, I did it backwards. No. Oh.
No, you did it right. You did it right. It's minus 8.
Outside times outside. Oh, I did here. This one and this one. Minus 8. Now we can group our like terms. There's only one x squared term. The x term has 4 minus 2. So that's 2x minus 8. In C, you're doing 3x plus 7 times x minus 5. And again, I'm going to write FOIL so that I get all of my terms and I make sure I do it properly. And you go ahead and do first times first. Then go ahead and do outside times outside. Inside times inside. And last times last. group your like terms.
First times first, first times last, second times first.
And you're done.
Yes, it is.
You liar.
I see you.
Okay, let's head off to example 3. Same principles will apply. It just gets a little bit busier with one extra step. So go ahead and rewrite question A in a place where you can do some work on it. And now we see that we actually have 3 factors. We have -2 out front, and then we have our 2 factors, which are binomials, inside the brackets. So this is the product of 3 factors that we're going to be finding. And the key to remember here is first find the product of the binomials. So first we're going to FOIL these guys, and we're just going to leave our -2 out front and multiply it by the answer in our next step. Okay? So we need to have a little equal sign here beginning our next statement. We're going to leave -2 out there. We're not going to deal with it yet. And whatever happens is going to still get multiplied by -2. So you don't need to draw this last bracket. I'm just showing you that whatever we FOIL is going to be inside here, and once we simplify, it's still going to get multiplied by -2 at the end.
Now we're using BEDMAS.
We are always using BEDMAS. BEDMAS never goes away. Always. Yep. But we're also FOILing. We're using our distributive property. So here we go with our 2 binomials. First times first. 4x times 7x. 28x squared. If you call out an answer, then don't call out an answer on the next one, so that somebody new has to call out every single time. Outside times outside is 4x times -6. -24x. Inside times inside, that's -5 times 7x. -35x. And then last times last is -5 times -6. +30. Good. Now there's 2 ways you can do this part. You can either multiply the -2 by every term inside the brackets and then group like terms, or you can group like terms right away. I see we have 2 terms named with an x variable, so I'm going to leave my -2 out here. Inside the bracket I reduce to 28x squared. Ooh, and then I have to group my x terms. -24 minus 35 is -59x's, and plus 30. And my last step now, I'm still using my distributive property, because this -2 has to get distributed to every term inside the brackets.
So you have to square the 59. You add it to x squared.
They are over here, like this answer.
Yeah.
It's not 59x squared because here I'm not multiplying the x's, they're attached by subtraction. Okay, so they're not, if x's were oranges, I'd have 24 oranges and 35 oranges. Right? So I don't end up with squared oranges. Oranges will still be round. Okay, here we go. -2 times 28. -56x squared. -2 times -59x. +118x. And -2 times 30 is -60 as our constant at the end. So 1 or 2 steps trickier, but not so bad after all. Let's do the last one, which is a multi-step one. I'm going to clear this. You double check that your b is the same as my b. I've got 2x plus 7 times x minus 3, and then minus 4x plus 3 times 2x minus 1. And right away you'll notice that this subtraction sign splits up the whole thing. So I'm not going to deal with these things together until the very end. Right now I'm going to deal with the product on the left, which has 3 factors, and then I'm going to deal with the product on the right, which has 2 factors. So here we go. Same steps as last time. I'm going to leave the 2 outside and deal with, I'm going to FOIL this. Okay, you go ahead and FOIL those binomials. And after you've simplified, probably will take you 2 steps, go ahead and just look at what you have and see if it's the same as what I have.
Isn't it 3x? Not 4x.
7x's minus 3x's is 4x.
And 7 times 3.
7 times 3 is negative 21.
Yeah, so it's, oh.
Okay, do the same thing for the 2 binomials on the right side of the subtraction arrow here. So foiling them again.
No, 7 times x is 7x.
Yep.
Not 4x.
And negative 3 times x is negative 3x. So I skipped a step. This is the simplified answer. So this is what you should have in the next step.
Never skip. What is this?
So here we got 8x squared, and it's in brackets.
Oh, I see what you did.
Oh, hee ho.
You're smart.
This is going to be 6x minus 4x. See that? 2 steps in one. Outside and inside. 6x minus 4x is 2x. And last times last is negative 3.
Text me your homework.
Excuse me. Now this 2 has to get distributed to everything inside the first brackets. Hopefully you're still staying ahead of me. I'd like you to stay ahead of me. Maybe I'll just pause for a second.
How did you get 2x minus 3?
Did you get positive 6x and minus 4x inside your bracket?
5x.
Oh, then you added instead of multiplied. Yep. Double check your next step and go ahead and check your answer. That is expanded and simplified. Way to go. Your homework is recorded for you at the bottom of the page. You have 4 minutes. You may ask, I would use that 4 minutes to ask questions.